Hello, everyone. Welcome to this week's Crunch seminar. Welcome from Providence, chilling Providence. Our first talk today is about condensation in deep learning. Our speaker for this talk is Zhiqin Xu. He's an associate professor at Shanghai Jiao Tong University. He obtained his bachelor's in physics in 2012 and a PhD degree in mathematics in 2016 from the same university. Before joining the current university, he worked as a postdoctoral researcher at the New York University, Abu Dhabi, and Corinth Institute from 2016 to 2019. With that, please join me in welcoming him for the presentation.
Okay, thank you. I will share the screen now.
Yeah, please.
Okay, can you see the screen?
Yes.
Okay. So I will thank George for inviting me to present our recent work here, and welcome to any comment. So I will mainly talk about condensation in deep learning, and I also talk some other works. So I really want to ask, its neural network is really so complex when I first see a neural network. So the universal approximation theorem tells us that a neural network with arbitrary width, it can fit almost any continuous function. So yes, neural network is complex. To understand the neural network, let's get started from traditional generalization theory. In traditional theory, if you have a function, it's very simple, and you want to do classification, you might get underfit. And if you get a function with very good power to express any function, then we'll end up in overfitting. So traditional theory said, if your function is too complex, then it's a trouble. But in neural network, here's an experiment. In this experiment, the neural network has a size about 1.6 million parameter numbers, and it can fit. Is used to fit 60,000 images. So the data number is much smaller than the number of parameters. So it can fit the training data with 100% accuracy. By traditional wisdom, in such a setting, it should overfit very seriously. But in such case, for neural network, its test accuracy is almost 90%. So it doesn't show obvious overfitting. So it seems that this overfitting trouble ignores deep learning. So we actually need to ask, is neural network really so complex in practice? Because the universal approximation theory is only in theory, it's not a practice. So we want to ask this question in practice. And in 1995, Leo Bremen, after reviewing papers of NIPS, he wrote a short paper and proposed several questions, such as why do not heavily parameterized neural network overfit the data? What is the effective number of parameters? Why BP does not hit for local minimum? And when should stop training? And these questions actually are still very popular in the deep learning theory now. And in this paper, he also mentioned mathematical theory is not critical to the development of machine learning, but scientific inquiry is. So in this talk, I will start from two phenomena and try to understand the deep learning and try to answer these questions. So the first phenomenon is frequency principle, and the other one is condensation. And I will briefly introduce frequency principle and mainly talk about condensation. So the frequency principle, we illustrated this phenomenon by a simple one-dimensional example. The target function here is the red curve here, and we use a neural network to fit this red curve. In the initial stage, the neural network output is this blue dashed line. And now let's take a look how it fits this target. So as we can see, it learns the landscape first, and after more and more training, it learns more details. So to understand such a training process, we study this in Fourier domain. And this red curve is the Fourier transform of the target function. This is the frequency, and this is the amplitude. And this blue curve is the FFT of the neural network output. Now let's take a look. During the training, the neural network first fit the first frequency peak and more high frequency peaks. So we summarize this formula by frequency principle, that is, neural network learns from low frequency to high frequency. So we then try to understand why there is frequency principle. The first key point is the decay of activation function in the Fourier domain. Now let's take a look at a very simple example. We use an activation function called a Richter activation function. It's like a Mexican hat. And we use such neural network to learn a target function with 3 frequency components. And in the spatial domain is illustrated by this blue curve. And this red curve is the initial output of neural network. We examine the relative error of the 3 important frequencies. This is the training epochs, and this is the 3 frequencies. And the color indicates the error. And we can see the first frequency converge very quickly, and the higher frequency converge very slow. And after training, at the training data points, the neural network does not fit very well, but it's still okay. And at the test points, it's also not so good, but also okay. And now we change. Okay, now there is a frequency principle, and we change this activation function. Okay, and we change an activation function with more sharp oscillation. So in the Fourier domain, you can see this activation function has more high frequency components compared with the previous one, right? And in this case, we can see there is no frequency is faster. So we let an activation function has more higher frequency components. In such case, higher frequency converge faster. But in such case, there is no frequency principle. In the test data points, we can see there is many oscillations. So we know that frequency principle somehow is very important to guarantee a smooth interpolation. Okay, this is the first key point. The second key point is the weight of frequency in the loss function. So we examine the 2 loss functions. One is the mean squared error. The other is we add another term. And this term is the mean square error of the gradient term with respect to the input. So in such case, for the normal case, we can still see low frequency converge faster. But in the second case, we can see that high frequency converge much faster, and there's all the frequency principle almost disappears. Why such phenomenon can happen? Because the gradient of the function with respect to the input in the Fourier domain is equivalent to this Cassie times the original Fourier transform. So this is equivalent to add more weight for high frequency. As some experiments, very similar experiments can also be found in the Lulu and George's paper, and also Professor Wenai's paper. So let's get back to these 4 questions. We know that this frequency principle is independent of network size, so it does not care about if it's heavily over-parameterized or not. And also, in many cases, early stopping can avoid fit high-frequency noise. So when one should stop the BP training, by the viewpoint of frequency principle, if the high frequency is noise, we should stop training at some early time before we fit it perfectly. So this frequency principle actually tells us that high frequency is very slow to be learned. So how to overcome this high frequency curse? We propose a method called multi-scale neural network. The idea is very simple. If a function is very highly oscillated, we can just stretch it. So it will become a low frequency function, right? So this just only need to perform this scaling in the spatial domain is equivalent to perform scaling, but just inverse in the Fourier space. So the network structure is very simple. Originally, for example, if we have a neural network, two-layer neural network with only three hidden neurons, originally we should set every neuron as A sigma Ws plus B, but here we decompose these neurons into three parts. In the first part is sim. In the second part, we add a scalar in this Ws. In the third part, we add a scalar in this 3 in this Ws. So it's just to stretch the function, the input function by different scalings. So you can use different structures by just implement this idea. We have one belief. We don't have any theory to guarantee the neural network will take advantage of this scaling, but we believe that the neural network at a gradient descent training will take advantage of every best way. And this activation function can be selected by very carefully. It will affect the performance. So here's an example that we solve on PDE in two-dimensional case. This is the exact solution, and this is the solution of normal function. You can see the solution is smooth. And if we use the same size but multi-scale, we can reconstruct the exact solution very well. And this structure is also adopted by many other literatures. And here's an example of Huawei Manifold Science tool. So frequency principle here provides a guidance for designing neural networks and a macro description of training. But for micro characterization of neural networks, we study the weight evolution. And this is also a main point of this talk. So now I will use a cartoon to illustrate what is condensation. So here is an example of two-layer neural networks. And this is input layer, hidden layer, and output layer. So at the initialization, the input weight or output weight of hidden neurons are random. And after training, we can see that the neurons in hidden layer are clustered. That is, in this case, the first two neurons, they are almost the same. They have the same input weight, but different output weight. And for the last three neurons, they have the same input weight. So the output of the first two neurons are same. Similarly, the output of the last three neurons are also same. In such case, this large neural network can actually be...
Zhiqin, can I just a clarification, because is this a single layer or two-layer? You were referring to two layers, but I see a single layer with 5 neurons. Or is it two? Is your present? I'm not sure what you're showing. The way you plot it is not conventional. On the left.
Yeah.
Can you explain to us what you are plotting and what you're considering?
Sure. The input neurons only have two. The input layer only have 2 neurons. Okay.
Right.
And the hidden neurons have 5 neurons. Okay. So this is the standard two-layer neural network, just like this.
Okay. So a single hidden layer. Yeah. Okay.
Yeah, that's right. I use this case as an illustration. So after training, we found that very interesting. If the initialization weight are very small, the neurons in hidden layer will be clustered, and in each cluster, neurons in each cluster, they are almost the same. So in such case, we can simplify this neural network to a neural network with fewer hidden neurons. For example, these 2 neurons will be simplified by this hidden neuron has the same input weight, but its output weight is the sum of these two neurons. So this is an illustration. Then we will use an experiment to demonstrate this cartoon. For example, we consider a two-layer neural network. Here is the formulation of this two-layer neural network. This alpha is set to 1, so we don't care about this alpha here. And this X is the input, but here we have a slightly abuse of notation. We incorporate this bias into this weight. So the weight here is the combination of original weight and also bias term. So this X here should have have a 1 here. And then we want to study the characterization of the evolution of this neural network. This is an inner product, so we care about the direction of this weight, especially when we study this ReLU neural network. The direction of this weight is very important. So we studied two components. One is the orientation of this weight, denoted by this W hat. The other is the amplitude of this neuron. This is defined as the product of this output weight and also the norm of the input weight. So for one-dimensional input, this X is one dimension. So the X used here is 2 dimension. So is the W here is also 2 dimension. For two-dimensional vector, we can use its angle to denote its orientation. So here's an example. In this example, we initialize the neural network on the width by the NDK initialization. We know that in NDK, with NDK initialization is in a linear regime. So our target function is 4 star here. And after training, the neural network can well fit the training data. And then we look at its characterization. This x-axis is the orientation of this W hat, and this y-axis is the amplitude. The cyan data points are the initial distribution, and the red data points are final distribution. As we can see that the final distribution are very close to the initial distribution. That makes sense because it's in a linear regime. The input, the initial weight and the final weight, they are very close to each other. So we can perform a Taylor expansion of the final weight with respect to the initial weight. Then we know that is the reason why we call it linear regime. However, the neural network's power is not in the linear regime. So to get a nonlinear regime, we initialize all these weights by much more smaller values. In such case, so this is the distribution of this A and W hat at initial and then final stage. So I normalize all this data, so you can see that the final distribution are very, very different from the initial distribution. In addition, the final distribution has a very, very special characteristics. So they are not so sparse. Their amplitude are somehow sparse, but more importantly, they have very sparse orientations. That means there are many neurons that have the same orientation, and they only have 2 groups of neurons. One group of neurons has this orientation, the other group has this orientation. Of course, we have a group of silent neurons. And that is the reason why we call this regime as a condensed regime, because neurons, their orientation condensed at isolated orientations. And if we take a look at their outputs, we can see their output are also very different from previous linear regime output. In such case, they have very sharp transition. Their features are very clear. Okay, so that is the condensation we can observe in training neural networks. So we want to ask what kind of initialization can lead linearity or condensation? If there's only very few kinds of initialization can lead to condensation, then condensation may be not interest. So we start in the first diagram of neural network. For two-layer neural networks, we can construct two statistical quantities that can characterize the initialization. And we found in the first diagram, there are only two clear regimes and a transition regime. In this blue regime is linear regime. Okay. Also note that this first diagram is started at infinite width network. And the other regime is nonlinear regime. If the neural network width is not so large, this transition regime will be larger, not just a line. So in nonlinear regime, we found experimentally that condensation is a common feature. So condensation is very important. So we also studied three-layer neural network. We also found, in addition to linear regime, there is also a nonlinear regime, and also the condensation is a common feature in nonlinear regime. So condensation is very important and it's very common in nonlinear training. So if a condensation happens, for example, in this case, originally we have many neurons, but actually in such case, two ReLU neurons are enough. For example, this ReLU and this ReLU, they combine together to get this final result. So naturally, we will.
Hello, Zhiqin. Can you hear me? This is Lulu.
Hi, please.
Yeah, I have one question. So, do you assume we only consider ReLU, or this also applies to other activity function? Also, what about the training method? Is this can I use SGD, Adam, or least square? So basically, what's your assumptions here?
Okay. So far, the experiment that I have shown are only for ReLU so far, and we have tried GD, Adam, SGD. They all have the similar experiment, and we also have performed experiment for sigmoid, tanh, and many other activation function. We can see similar condensation when the initialization are small. Okay, that is my answer.
Okay, thank you.
Okay, so once we see this condensation, naturally we will have a question. If the original network is so large and after training, it gets to a very small neural network, why do we not just train a small neural network? Why do we need to use so much computational cost to train a large neural network? Do they have any similarity or any difference? That is the thing we want to study. So we train a neural network with different widths. And here is the loss function of our training. The target function is all these blue star points. And we use neural network of like width 1, 2, 3, 4, and so on. And the loss function shows highly similarities. They have this plateau at a similar position, similar loss values, of course, different training epochs. And for example, at this plateau position, this flat position, their output are very similar and they have very similar condensation. So we know that neural network of different width, they will go through some same point in some sense. So how to study this point? So we study a nano neural network and a wide neural network by this embedding rule. So in this embedding, in this small neural network, we split these neurons, these black neurons, and we split it into this blue and purple neurons. And we copy its input weight from these black neurons. So this is the condensation actually. And its output actually is also split by the output weight of these black neurons. So the L+1 layer neurons in this layer have the same input from the previous layers, because this blue and this purple, their summation is equal to this black neuron. In such case, we can prove that the output of this nano neural network is the same as this white neural network. This is a natural result by our construction. And key point is we've proved that if the nano neural networks is in a critical point, such as a saddle point or local minimum, the white neural network is also in a critical point. But the nano neural network can be in such as in saddle point, in local minimum, but this white neural network can be in saddle point. They can be different. So we prove an embedding principle of neural network loss landscape. That is, the loss landscape of any network contains all critical points of all nano neural networks. The proof can be by the following construction. So based on this embedding principle, we further prove that for a larger neural network, it almost have more descent directions. So this theorem actually points out that if you embed a neural network into a larger neural network, originally it may be in the local minimum, but because it has more descent directions, so it will become a saddle point. If a critical point has more descent directions, it may be easier for training. So we have a comment here. Maybe wider neural networks is easier for training in some sense, because it's not in the local minimum, maybe go through saddle points with more descending direction. I have done many experiments of feeding high frequency functions, and I found that if you use very nano neural networks, it's very hard for training. For very, very long time, the loss function just does not decay. But if I increase the width or the depth, it will the loss will decrease much easier. So this may be helpful for understanding why the neural network does not head for a poor local minimum. So the following, I will talk about what condensation benefits in generalization. So previously, I have shown this puzzle that in neural net, in deep learning, even the number of parameters is much larger than the number of training data, but it always generalizes well. Why? So actually, we asked the question, is there really so many effective neurons in large neural network? Our previous examples show that although the original neural network has so many neurons, but after training, its effective neural number has only 2. So what benefits the condensation can bring for generalization? That is, the effective neural number are actually much smaller than its real number. But okay, this will help us to understand further why don't heavily parameterized neural network overfit the data. That is because if a neural network has condensation, then the over-parameterization is not an issue anymore, because its effective network after training actually is small. So this actually brings some other theoretical issues. Traditionally, we usually compare the number of data size and the number of parameter size. If the number of data size is larger than the number of parameter size, then we know it will generalize good. And now we have condensation, and the number of parameters are not important anymore. So how can we know how many number of data are needed for guaranteeing the good generalization of neural network? To study this problem, we start from traditional linear regression. So now let's take a look at a very simple example. This is a linear model, and we use linear model to fit several target functions like 1, x1, 1 plus x1, and so on. And we sample different data size and then use this model to fit this data. For example, if we try to fit the target function 1, and we sample the several data points, of course, the output is a constant, but the input can be different. And unless we sample 3 data points, the error, the generalization, the test error can be very, very small. Similarly, for other target function, we always need 3 data points to perfectly fit the target function. This is very easy for understanding because this is a linear regression. We need the number of data equal to the number of parameters. But now we make a slightly change for this model. We use a nonlinear model, and we use more parameters. In this model, we just replace the previous theta 2 and the product of theta 2 and theta 3. So in this case, we have more parameters. The model is more complex, but actually during the fitting, we found a very different thing. If the target function here is 1, x1, or 1 plus x1, we only need 2 data points. Then the test error can be very, very small, almost to the machine accuracy. But for some other target function, we still need 3 data points to perfectly fit the target function. Now let's take a look of the fitting result of the first 3 target functions. So for example, for the target function of constant 1, after the fitting, the value of theta 0 is almost exactly equal to 1, and other parameters almost equal to 0. So it did perfectly reconstruct the target function. For the target function x1, only the theta 1 equals to 1, and others almost equals to 0. So it also perfectly reconstruct the target function of x1. So now we have questions. We have more complex model, but we have less data, only 2 data.
By the way, Zhiqin, so what if your start with not a small initialization, you have order 1 initialization?
Okay, if we start with like a large initialization, then we still need 3 data points to perfectly reconstruct these 3 target functions. Correct.
So is this for small initialization, you have theta 2, theta 3, essentially you have squared. Then for theta 2 and theta 3, you
The
do
key point here is square, right? That's right. Yeah. I will analyze this point later. Yeah, that's the key.
Okay, thank you. Yeah.
Okay, sure. And we have different target function. The different target function, they have different data required. Why? So now let's get back to this linear model for recovery. So for linear regression, we know the number of data should be larger than the number of parameters to guarantee a good generalization. For example, and also for example, the Nyquist shallow sample theorem also have similar requirement. So in traditional machine learning, we have this overdetermined or underdetermined regime by just compare the number of data and the number of parameters. If the number of data is larger than the parameters, then this is overdetermined. Otherwise, it's underdetermined. So in this traditional learning theory, if you have many data, many parameters, you will easily overfit. So this is what we know. So for this linear regression problem, so how can we understand why it requires 3 data points for this model. So we can write this model by the following tangent space form. So suppose we perform a local recovery, not a global recovery. So around the global point. So we can write in the model in this form. This is the target function, and this is a perturbation. It is a neighborhood. So this actually is a linear space. And in linear space, it has three independent bases. So how can we determine a point in a three-dimensional linear space? Of course, we need 3 data points because its dimension is 3. So this is a local recovery theory. Now let's take a look at a very any model, any linear or nonlinear, and we also consider this local recovery. So how can we define the effective size of parameters for a model at a local neighborhood of data parameter, for example, at a global point? So we can perform this gradient of the function with respect to all parameters. Then we get a tangent space, and we count the number, the dimension of this tangent space. That is how many data we need to locally determine these parameters. So this is how we define the rank of a parameter. Then we defined the rank of a target function in the model. So for a target function, we have a lot of parameters that can fit this target function. And every parameter, it has a rank, and we take the minimum rank as the rank of this target function. So what's the meaning of this definition of the rank of target function? That actually shows the minimum number in any case, almost at random any case. If you perform a local recovery, the minimum data point required to local recover this target function. So this is a very simple linear analysis. Now let's get back to this linear and nonlinear model. For this nonlinear model, we can perform the rank analysis for each parameter. So for any theta, we can perform this function to any parameter. For this one, you get 1. For this theta 1, you get x1. For this theta 2, you get a theta 3 times x2. For theta 3, you get this theta 2 times x2. So for this case, its dimension of tangent space does not fix. It's not fixed. If theta 2 equals to theta 3 equals to 0, its dimension is 2. Otherwise, it's 3. Now, let's take a rank analysis over the function space. For the target function in this A0 plus A1 times S1, its minimum dimension of tangent space is 2, so its rank is 2. And for other situation, its dimension is 3. Now, if we perform rank analysis for linear model, its rank is always constant, equals to 3. So what's the meaning of this rank, this dimension of tangent space? The key point is following. So if you have a global point, it has a tangent space of only dimension 2. That means in the neighborhood of this point, you only need 2 data points. Then you can local recover this global point. However, for this case, it has 3 dimensions for its tangent space. If you have only 2 data points, you cannot perfectly recover the target function because the dimension is too large. So if you have only 2 data points and you you have two situations. One is in the local neighborhood of this global minimum. The other is in a neighborhood of this minimum. Then only this case can recover the target function. So this is the theory in local recovery, and very simple. But we have a bold assumption here. We assume the following linear stability hypothesis. So if you are using a very nonlinear training, then the training will prefer linear stable point. For example, in these two cases, if you have only two data points, and these 2 points are both global points, but we guess that the nonlinear training will lead the neural network to this point, but not this point. So this is a hypothesis. You can challenge this because this is a local recovery, but we actually care about global recovery. But we will show a case that neural network will obey this linear stability hypothesis. That means it will prefer linear stable point.
Sorry, Zhiqin, could you just clarify, so what do you mean by nonlinear training?
Okay, so I don't have a very clear definition of nonlinear training here, but for neural network, as I have mentioned, if you initialize the neural network in the NDK regime, the feature of the weight does not change so much, then it's a linear training, right? So if you initialize the weights with very, very small values after the training, the weights will be very different from the initial value. Then this shows a very nonlinear behavior that we define this is a nonlinear training. In my talk, the nonlinear training actually means the condensation happens. And I will get back to this point to explain why there's a condensation happens in nonlinear training in a specific case.
Zhiqin, I think there is this type of analysis is in clear contrast with information bottleneck theory, because what you are looking at is training, and training, you mean you fit the data and your training loss goes to zero. But if you look at the information bottleneck theory, it's just a phase transition. Right when your loss function is zero, if you run it for a long time, that's called the diffusion stage,
yes,
you will get the fluctuations of the weights with norm 1, the gradients actually, the gradients of the fluctuations of the weights, while the mean weights are zero. So you're looking at the mean weights, and that's fine and everything. But so therefore, that's why it's called the diffusion part. It's called the learning part, because when after you fit the data, which is basically what you're doing, and you do this analysis, you say, I'm done, and I know my system, it's condensed and everything is good. But it's not true, because the generalization, which is associated with true learning is really during the phase transition and the diffusion regime, where you will visit other parts of the landscape, of the loss landscape, and therefore you will destroy the condensation that you had there. That's why the overparameterization is really important. So even your definition of linear versus nonlinear, it's true only up to the point where you're training, not necessarily when you're learning. So you have to be careful about the learning problem. I don't know if you know the work of late Professor Tishby from Israel, but that's what he was talking about. He was talking, there's an advection phase, and then there's this phase transition, the diffusion phase, where you're actually learning. When you're learning, you're dealing with fluctuations because of stochastic gradient descent, the way we do the mini batch and so on in linear. So if we believe him, then condensation probably would never happen, because it would happen and then you go to zero. I have a plot to show you if you want from his work, but then later on, all these neurons will pick up noise that then eventually will become non-zero, so they will have their own identity. So it will not be like clusters like you have. You know what I mean?
Yeah, I understand because actually when we first do the work of frequency principle, we try to understand the phenomena of the information bottleneck. They have proposed this phase transition, phase 1 and phase 2. One is a compression phase. We can understand this from this frequency
The
perspective.
compression. I think the compression stage now of the offsprings, the later papers by his students and others show that the compression stage doesn't always happen, but the diffusion phase is always there. But the interpretation, which is compression, sometimes it may happen, sometimes it may not. So that's a little controversial. But I think the fact that you fit the data, which you sort of do, and you say, okay, now I have these clusters. What I'm saying is that this clustering, this condensation stage may not be stable. So if you run further, even though you are at zero, close to zero, your loss function is zero, because this diffusion that happens, you may pick up other clusters. That's all I'm saying.
Yes. Yeah. Thanks for your comment. I want to add more comment. This diffusion process in the information bottleneck paper, it requires this SGD very much. It depends on this stochastic gradient descent very much. So we, in my talk, we actually can constrain our all analysis into this gradient descent. So so we can maybe forget this diffusion stage for now. We only have some experiment to show that.
Yeah. I agree. Your analysis is correct. I'm not saying that your analysis is not correct, but what I'm saying for the real problem, the condensation phase, you sort of go from the initial stage, from the linear to condensation stage. That stage, what I'm saying in a real problem, where you use mini batches stochastic gradient descent, that may not be stable. But what you're doing is fine. It's just that I'm not sure that relates directly to the learning problem.
Okay. Thanks. Okay, I will continue.
Yes. Sorry, I misspoke. It relates to the learning problem, but I'm not sure it covers it fully. That's what I wanted to say.
Thanks.
Please continue.
Okay, thanks. Okay. So in the previous example, we have shown that in this case, so if the target function is 1 plus x1, if we learn this problem by very small initialization, you will finally learn the solution of A0 of this theta 0 and theta 1 as well, but not the other solutions. So this at least in this case fits this linear stability hypothesis. So our analysis actually try to point out a new regime beyond this traditional regime. So traditionally, we only have this overdetermined regime and also this underdetermined regime. But for nonlinear model, actually, there is a quasi-determined regime. In this quasi-determined regime, this number actually is smaller than the number of the actual parameter number. And this quasi-determined regime, this learning has potential or has possibility to perfectly fit the target function. But as mentioned by Lulu before that, if we initialize it with very large values, our experiments also show it will deviate from this true target function more. So we call it quasi-determined regime, means it has potential or it has possibility to reconstruct this target model by the number of data points smaller than the number of parameters.
Can I quickly ask a question? This is Eunbyung from KAIST. Hi. So I'm not sure how the rank is being defined precisely. It seems to me that it's highly depending on what target function and what your basis functions to be. For example, if your target function is x squared, it seems to me that rank is not defined. So that can you a little bit clarify how this rank being defined?
Oh, sure. Okay, so first we actually have a an assumption here. The target function should be in this model function space. So this assumption, I think it's natural because if you have several data points, we always assume that the neural network is power enough to fit these data points. So after the training, the neural network, we use a function to fit this these few data points. So so we have this assumption that this f star in this model function space. That is the first one. The second one is this rank definitely depends on the target function and also depends on, for example, the rank of a parameter also depends on the which parameter you are considered. For linear model, it's a constant, but for nonlinear model, it's not a constant. That is why we have possibility to use the number of data less than the number of parameters to fit the target function. Okay, that is the two answer for your question.
Okay, thank you. Then ideal case is the rank shouldn't be 1 then, because our space is already have all the parameters, so that, I mean, target function included, so that.
Yeah, ideally we expect that the rank of the target function should be very small. Then the data we need is also small. We can perfectly reconstruct. That's if I understand it correctly.
Then in ideal case, do we only need a 1 point then?
No,
If the rank is 1?
No, yeah, if your target function is very complex, you definitely have no choice, have no chance to only have one data point. You can, okay, if your model is somehow very close to your target function, your rank can be very small. Yeah, then you can use very few data points to perfectly reconstruct it. And I will show some examples later.
Okay, thank you.
So here's an example of the rank analysis for neural network. So consider a fully connected an L layer neural network. And if your target function is in this model space, and the rank we calculate here, you can see that the rank is independent of the width of the network's width. So this shows that you can use a very large neural network, but actually the rank for a target function is fixed. So if we admit this linear stability hypothesis, then the number of data we need to for training this neural network does not change if you increase the width of the neural network. So this is a very good property. So we don't need to worry about if we use a very large width neural network. So here's an example why we can have such property. As I have shown that if a neural network after training, it can condense, then these two neurons, they are clustered in a same group. So their input weight are the same. If the input weight of these two neurons are the same, then the tangent space of these two neurons actually are the same. So they are same as this after this simplified neuron. So the tangent space of this large neural network actually is the same of this small neural network. Then we just need to count the tangent space of this small neural network. And we know that no matter how large of this original neural network, after it condenses, the number of effective neural network matters. So this the dimension of tangent space of this small net matters. So you can use over parameterized neural network to fit the data, but after condense happens, the the data you need to well fit your target function actually does not change. So here's an example.
But I have one more question here. So why try to compute the rank? So in practice, these two lines can be close, but can never be exactly the same, right? So
Yes.
they are not exactly the same. The let's say the basis function.
Yeah.
So if you try to compute the rank, so yeah, cannot be reduced. It has some epsilon thing.
So let me answer this question first in ideal case. So we know that in statistical mechanics, if you only have very few particles, you cannot have this phase transition clearly. But if you have this so large number of particles, then you will have this sharp phase transition from this solid stage to like a liquid stage. So when we study this so-called tangent space analysis, so we actually are studying some linear, some ideal case. So you mentioned that if two lines are very close, very close, but they are not overlap exactly, so the tangent space may be maybe large, but actually during the training, they can be reduced to the same line. So when we study this tangent space analysis, actually we try to study the ideal case. So for example, in the neural network training, actually they are not condensed exactly. But if we have the infinite ways, it can condense very clearly and very obviously. Neurons are almost exactly the same. In such case, we can perform analysis. But during the real training, we have finite ways. They are not exactly the same. However, the results are very close to the ideal case. And I will show an example. For example, in such examples, the number of data we theoretically predict is this blue dashed curve. But in real training for very large neural network, actually the number of data to make the test error very small is not exactly the same with this prediction, but they are very close. So I agree with you that the exact case in real training may not happen, but this can be an approximation for us to understand this phenomenon. So this is the motivation why we perform such extreme analysis, or very simple analysis. Okay, so here's an example try to show that the benefit of such analysis. For example, if our target function is a two-layer with K convolution neural network, we can use a convolution neural network or use a fully connected neural network to fit this target function. And first, we can compute the rank for these two models for this target function. And we can see that the model rank of the fully connected neural network is much larger than the model rank of the convolution neural network. The key reason is, although in a fully connected neural network, the weight is 0, but it has a non-zero tangent space. After we perform gradient of this 0 weight, we can still get a non-zero function basis. So in this case, we can exactly compute that the fully connected neural network requires almost 1,000 times more than convolution neural network. And so here's an example. This is the target function weight. And we use a fully connected neural network convolution without weight sharing or convolution with weight sharing to fit this target function. So this is the same size of the target function. And this dashed line is the prediction of how many data we need for such a structure. And we can see that for the test error, this is the sample size, and the color indicates the test error. So we predicted that after the data size is larger than this dashed line, then the test error will be very small, and the experiment is consistent with our prediction. And if we increase the size of neural network, for example, for this fully connected, other 100 times of the original size, we can see that the number of data we need actually does not increase so much so as for other structures. So this means that when we use very, very large neural networks, we actually don't worry too much about this overfitting issue if we are training a neural network in this nonlinear regime. So there are many long-standing problems like the over-parameterization issue, or the number of effective size of parameters, implicit bias of a nonlinear training. When a CNN is better than fully connected neural network in some case. But the key point to understand all of this is like why the linear stability hypothesis can be right. That means in nonlinear training, the neural network can prefer those linear stable points. To understand this, we actually give an example to show that why condensation can happen. If a condensation can happen, we only need to count the dimension space of this condensed neural network, but not original large neural network. So we don't have too much work about why condensation can happen, but we found a very special case that is dropout. If you have a dropout trick during the training, it can facilitate the condensation in the whole training, and that is very interesting. So let me very quickly introduce this part. So the dropout means during each training step, we randomly throw out some neurons. So here we times random variable for each neuron, and this random variable can be 0 with some probability. So we also train a 2-layer tangent neural network. Without a dropout, we initialize the neural network with very large numbers. That means the neuron is initialized in a linear regime, very similar to decay regime. So after training, you can see that the neural network can fit the data points well, but it has a lot of oscillation. And we also know that in such a linear regime, the neural network will not condense. But if we add dropout during the training, we can see that after the training, the neural network can also fit the training data points, and seems has a flatter solution. And let's take a look at this feature distribution. For this case, without a dropout, the initial distribution and the final distribution, they are also quite close, not so different. But if you have this dropout, you can see after training, the neural weights, they are condensed very well. So the dropout can facilitate the condensation. So we also performed an example for 3-layer tangent network. You can see the condensation similarly. We also want to mention that if you only use SGD in such a linear case, the condensation will not happen. So we try to theoretically understand why dropout can facilitate this condensation.
Hi,
Please.
Esan from Carbon. Can I ask a question on previous slide? Can you go back to the slide that you had the weights comparing with dropout and without dropout?
This one, right?
This one, yes. So I just try to understand the figures on the right. What is the vertical axis? Is just the value of the weight?
Oh, no. Let me go back to this one. Maybe easier for understand here. Yeah. So this x-axis is the the orientation of this weight. Each point is 1 neuron. And
Yes.
this y-axis is the amplitude of each neuron, the product of input and output weight norm. Okay.
Okay.
So if you have condensation, that means the weight have only have isolated orientation, such in this case. After training, the orientation of weights only have two values. Okay. So that is condensation.
Mhm.
So in this case, so we initialize neural network in linear regime. So if you only use gradient descent training, you will not get a condensation. But if we have a job out trick during training, you can see the weight will condense very clearly. Okay.
And does this mean lots of weights in the ultimate train network are just zero?
That means there are only few effective weights. Okay. Here.
Mhm.
Yeah, few effective weights. And
Okay.
some weights are zero.
It's not zero. Okay, thank you.
Yeah, but this
So-
initialization is large initialization, right? If we use not use small initialization, probably the standard training without dropout still works.
Yeah, still works. Yeah, just like previous case. Yeah, if you use very
Okay.
small initialization, you will condense anyway. Yeah.
Okay. Yeah.
But to see to be clear, to see the effect of dropout, so we initialize this in the linear case. So we compute the modified gradient flow of dropout training. So the loss function of dropout training, the expectation with respect to this random variable can be explicitly computed. So this RS term is the mean square error term. And we have two extra terms, an R1 and R2. So this R2 is not so does not have so much effect. This is due to the discretization. And there are several other studies have studied this R2 term. So the new term is R1. So we will study what's the meaning of R1. Okay. So we use a very, very simple case, 2-layer neural network, and also two neurons, only two neurons. So the target data, only two data, and the target function is the activation function. So we have only two data points. So if we can perfectly fit the target function, that means for each data point, the model output equals to your label. For the first data, that means sigma x1 should equals to this model output, and also for the x2. So after perfect training, so we can write this perfect training formula into the vector form. We put these two terms into a vector, and this two can also this one and this one can be in the the first vector, and this two can second vector. Then we denote this as the O star, and this one is the O1, this one is the O2. So this O1 means the output of the first neuron is these two data points. This O2 means the output of the second neuron at the two data points. So after training, we should have this O star equals to O1 and plus O2. That is the requirement of this mean square error. But we still have this actual term R1. This R1, this formula, in this setting, we can compute it. That equals to the L2 norm of this O1 and the L2 norm of this O2. So let's take a look at a very simple case. Suppose we have two situations that satisfy this first this equation. That means it can fit the target function. So this the pair of this yellow pair and the red pair, they have the same summation. But if we compute the R1 regularization, we can see that this yellow pair should have larger R1, but this red pair should have smaller regularization term. So this, if we want to minimize this R1, the best case is to let this O1 and O2 parallel. So once they are parallel, that means they have the same orientation. Then they will condense. So this simple case actually shows why with dropout, the neural network can have this condensation during training. So if we have condensation, now we can predict how many data points, if we have a target function, how many data points we need to perfectly fit. So this is so in this case we predict 5 data points as required. So if we have a dropout after we have more than 5 data points, then the error will decrease to a very, very small value. But if we don't have dropout, we don't have this condensation, you need many, many data points. So this example shows the condensation can have some benefication in generalization. So now let's get back to this 4 questions. If we have this rank analysis and also condensation, then we know that heavily over parameterization is not so important. And this rank analysis can help us calculate the effective number of parameters. So we have a few works of understanding this condensation. We have another work of understanding why there is an initial condense, but not the whole training process for gradient descent training or SGD, or in the dropout in any hidden layer. So previous case, we only have theoretical explanation when the dropout is in the last hidden layer. But our experiments shows the phenomenon of dropout in any hidden layer. And there are many other works are not clear so far. So in this talk, I actually briefly introduced the neural network length from low to high frequency, that is frequency principle, and also talk about in nonlinear training, the neural network usually have a condensation. If the neural network is initialized very, very small and very wide, this condensation will be very obvious. And this is the advertisement for Journal Machine Learning Journal. The editor-in-chief is Professor Wina Yi. And this is an open access and there's no fee for publication. We have faster yet a thorough review process. And this site is very easy to be remembered, JML.pub. So I want to thank my colleagues and my friends and my teachers, advisors for this these works. Thank you.
Thank you, Professor Xu. We already had a lot of discussion during the presentation. Maybe so let's thank him for the presentation. Do we have more questions for the speaker?
Sorry, yeah, I just want to ask one quick question. I was trying to save mine for the end. Your philosophy for this whole presentation, right, is that you want to look at a standard MLP and you train it and you want to understand how condensation occurs. And then you look into dropout as a mechanism for how to promote condensation faster. One thing that my group's been interested in is, can you design an architecture to facilitate condensation in training? You know, there's lots of other works that have tried to do things like take a train network and then condense it up. But over the course of the training process, maybe you can do something in architecture. I suspect you know the literature really well. I'm curious if you're familiar with anyone, you know, as opposed to trying to do it through dropout, can you do it through architecture design? How to approach the condensation problem? Does that make sense?
I understand this. Your question may be, how can we design the network structure to facilitate this condensation, right?
Mhm.
From my understanding so far, maybe not very clear or many. I think the initialization is very, very important for this condensation. And this condensation can happen for almost any structures we have used, like this CNN, but we don't know, like transformer, we don't test it. Standard MLP, and if we can design the structure can facilitate, I don't think if you don't have a good initialization. And this is the first point. The second point is the structure, I think, is very, very important, especially when a condensation happens. If your structure is very close to your target function, very close to a target function, and you have condensation, then the number of data points, the samples you need will be very, very small. So in such case, I think design a good structure is very important. Yeah, that's my.
Okay, great. Thank you very much. Great talk.
I have a question for so how about the L1 regularization? Because with L1 you promote sparsity, and of course dropout does the same thing, regular, but L1 is more clear, is more direct way of condensation, promoting condensation, right?
Okay.
The L1 decay and L1 regularization, yeah.
Yeah, sure. Yeah, here, for example, for this case, so you can see that there are many neurons that their amplitude are 0, right? So if you have L1 regularization, for width, maybe there will be more neurons that have 0 amplitude. So, but the sparsity of the orientation cannot achieved by the L1 regularization of the width. Yeah, that is different sparsity. One is the 0
So
or
you mean
non-zero.
you mean you don't affect the direction, like, because okay, so then this is consistent with what Nat Trask asked you, because the architecture, right, with the basically what you're doing with the dropout, you have different architectures. You sample different architectures, and therefore you affect the angle, the rotation, as opposed to L1 where you you make the amplitude small for fixed directions of the vector.
Yes.
You can think of that way. Maybe.
Yeah, that's right. Yeah.
Okay. Thank you very much.
Thanks, George.
Thank you, Professor Xu. So we maybe we'll move into our second speaker. Professor Xu,
Wait, the share.
Yeah.
Thanks.
So our second speaker today is Dr. Eunbyung Park. He's an assistant professor in the Department of Electronic and Electrical Engineering at Sungkyunkwan University, South Korea. He has obtained his bachelor's degree in computer science from Kyunli University. His master's degree is in computer science from Seoul National University, and his PhD degree is from University of North Carolina at Chapel Hill in 2019. Before joining this current university, he was a research scientist at Neuro and an applied scientist at Microsoft. His current research interests include machine learning and its application to visual and scientific computing. And he would be talking to us about separable PINNs, mitigating the curse of dimensionality in physics-informed neural networks. With that, please join me in welcoming him for the presentation.
Thanks for the introduction. Can you hear me?
Yes, we can see your screen and we can hear you perfectly.
Yeah, so it's my great pleasure to be able to give a talk at Crunch seminar for University. So yeah, I'm Eunbyung Park. from SKKU, South Korea. Actually, we are 3 a.m. in the morning right now. So I don't think I have a clear mind at the moment, so please bear with me. So anyway, I'm kind of newbie to this field. So my background, as Sumata introduced, computer vision and machine learning. And for some reason, I got interested in this field, and I started working in this field since I joined SKQ as a faculty. So maybe about 1.5 years, 2 years so far. So the reason I'm saying this is because I'm 100% sure that the most of the audience in this talk knows much better about PD's physics, also PINNs than me. So don't hesitate to make some comments or correct if I'm making some wrong statements. And I also invited the co-author of this paper. So they might be able to answer the question that I think I'm not the right person to answer. Okay, so let's get started. So today I'm going to present Seperable PINN, so mitigating the curse of dimensionality in PINNs. This is an extended version of the paper we published DLDE during the last year workshop. So this talk includes the context in the paper, also some of the recent progress we've made so far. And this is a collaboration with Jhiqin Xu, Sungkyunkwan, Eunbyung, and Eunbyung, Jhiqin Xu, and myself. Okay, so I guess most of the audience in this talk know what the PINN, so I'm just gonna quickly go through what the PINN is about. The PINN is just a neural network approximated function U, and we are using automatic differentiation to take the derivative, the du dt, du dx, and also higher order gradients. And given the PDE that we are trying to solve, so that's going to be our loss function, and we use general optimization algorithm such as ARAM or AFGS to minimize the PD residuals. And eventually, what you get is the neural network parameter setup, and neural network is approximating solution function U, satisfying PD residuals. So there's PINNs, and PINN has pros and cons, and there are several lists that I displayed here. So it's first mesh-free solution, which is really great. If you think about some adaptive FEM methods, we have to consider how to construct a mesh structure, and that really affect performance of your solution. And
excuse me, can you speak a little closer to the microphone? Thank you.
Now it's okay.
Yes, thank you.
Yes, I was trying to say the pros and cons of the PINN, and PINN is a mesh-free solution, which is great, and also it uses automatic differentiation, and also neural network training. So I think it's easy and also very accessible. And if you think about TensorFlow, PyTorch, and other deep learning software library, we have a lot of rich software ecosystem, so people really can build top of the other people's work. I think this is really important. And also we can use the same optimization framework for both forward and inverse problem. And from my experience, like few lines of code, we can solve forward and inverse at the same time. And also from machine learning perspective, it's unsupervised learning compared to operator learning works. In operator learning, we have to collect a large set of solution examples that also come from the numerical solvers. And if you don't know about how to solve PDs, then in the first place, we don't have data set, and we can't actually train the neural network. A PINN is completely unsupervised learning, so which is also very great. There are also some issues, and first, the previous talk also a little bit talk about this, and neural network has some spectral bias. it tried to learn low frequency components first, and then eventually they tried to learn high frequency components. People came up with a lot of tricks to avoid those issues. For example, positional encoding, also sign activation functions, but they still rely on neural network. And we, as far as I know, we don't really know how to control neural network bias very well. And sorry, my voice is. And it's relatively slow from my experience. And also, obviously, it has some cost of dimensionality, and this talk, I'm going to focus on this part. So number of training points. So if you think about high dimensional PDE, so this is 1D, this is 2D, and this is 3D. And I believe I present 10 points here. So as the dimension increase, the empty space between collocation points gets larger. So the higher dimension, the more collocation points are required. So technically, the number of collocation points can increase exponentially. And it's not also about only dimension. It's about the complexity of the solution function. And this is an example of 2D Navier-Stokes equation in turbulence regime. And if you have few number of collocation points, for example, this point and this point, and then there's no way you can actually accurately interpolate the function values, because there are a lot of high frequency components between these 2 points, and neural network has some spectral bias, and they probably make some smooth function between these 2 points, or some empty space between the few collocation points. So we have thought about the way to employ the massive number of collocation points in training pins. So this is the suggested architecture, the separated architecture. So in conventional pin, we have one neural network, right? And that neural network takes coordinates from all dimensions. But in this separated architecture, for example, 3D PDE, we have 3 different neural networks, and each network has different parameters. So these 3 networks are different functions, and each neural network outputs here r-dimensional vector, and here I will explain later, but I'll sometimes refer to rank of the approximate solution, but I will get to that later. And so this is r-dimension, and second network also has r-dimensional vector. Also, third network has r-dimensional vector as well. And then we do element-wise product. Then 3 r-dimensional vector becomes 1 r-dimensional vector, right? And then we sum up the all elements in that vector. So we'll output 1 values here. That this is a separable pin architecture, and if we write down as an equation, then U of X becomes sum of j equals 1 to r, and each r is a product of output of each neural net. So that's a separable pin architecture. And obviously, we are not really processing point by point when we train pin. So we usually do batch, right? So we put a lot of input points to the network, and then we somehow model the relationship between the solution values of different collocation points to get the solution, right? So in separable pin architecture, let's say we have n training points for each dimension. So here's let's say n coordinate, so n points for the first dimension, and then another n points for the second dimension, and another n points for the third dimension. So as I previously mentioned this neural network outputs r-dimensional vector for 1 point, and now we have n points. So this neural network outputs n r-dimensional vector, so which displayed here, and we have 3 of them. So here we are solving 3-dimensional PDE, and then we do outer product between these vectors, and we have all of these guys. We sum them up, and then we finally reconstruct the solution tensors. So this is how we construct the solution function, and obviously this is if you are familiar with singular value decomposition, basically this is what it is. So we can interpret separable architecture solution as a low rank approximation of the solution tensor if the solution tensor is discretized. So the effective number of collocation points in this case, for first dimension we have n points, and second dimension we have n points, also third dimension we have n points. So we have total 3 times n network evaluation to get this 3-dimensional tensor. And so effectively the total number of collocation points we actually produce is the n to the 3, so n cubic. So that's the magic here. So we actually generate n to the d collocation points, but we only evaluate n times the number of network propagations. So that's a batchified processing of separable PIN architecture.
Hi, this is Kamal. Can I ask you a question? Previous slide.
This one?
No, previous. I'm Kamal from Grants Group. So the next one. Next one. Yeah. No, the architects.
This one?
No, next. Where you have shown the number of points.
Here. Maybe there's some delay.
Yes. So is there any restriction about the n? Like, is it has to be same in all the 3 direction?
No, it doesn't have to be.
And any restriction about the discretization uniform or non-uniform also?
No. Theoretically no, but when you actually implement this one, there might be some restriction. For example, we do the same n for all 3 dimensions, but that just depends on the implementation, but no restriction.
Okay. Thank you.
Hi, this is Amir from Brown. I have also one question here. Yeah, in this slide, you have shown that for each input point, say n, you have n times r vectors. That's the output of the network for each dimension, right? And then what you are doing is you are doing the the element-wise product of, say in this case, x1, x2, x3. So you have element-wise product of these r vectors, right? But on the top, if you see, it looks like it's basically a tensor product, not the element-wise product. So am I missing something here?
You're correct. So this is a tensor product. So to compute the 1 point here, also these 3 values are multiplied, and also this value also multiplied by another element of another vector in the another dimension. So it's like a Cartesian product, right?
Okay. But in the previous slide you mentioned you are doing basically the element wise.
Yes, I think we are the confusion control. So here, when we compute just 1 point, then it's just product of outputs of the different network. But when so here, let's say, but we have to do some batch processing, and then it becomes this form. I'm not sure if I explain correctly.
Okay, thank you.
Yeah.
I have a question. Dr. Park here. Can you go to the previous slide? What is the dimension of x1 here?
This just scalable.
And there you showed x1 as a vector, transpose vector. So they are not same.
Where is the x transpose?
In next slide. Yeah, here you see x1 as a vector.
Here x1 is vector. Yes, you're right. Sorry.
Yeah. So
it's a multiple axis, right?
Yeah. So one question. So means here I fail to understand here, like each element in the x1 vector will have r dimensional vector as an output. Am I right?
I think so.
Okay. And this is not element wise product. This is tensor product. Because if you have this situation where each element, so you will have like for first two products, suppose you have XYT, so it will be tensor product will give the dimension of R cross R.
I think so. Yeah, you're absolutely correct. So yeah, I think there's a confusion. Sorry. So when we process one point, it's element as product, but when we have to handle multiple coordinates, that's going to be tensor product.
Yes, can we go to the previous slide? Because I spent a lot of time to figuring out all these dimensions and I was lost. So here you have suppose this is R vector. So for each element you have a R features that you mentioned in your paper as a encoding of the input. So this will give the tensor product. So R cross R, this matrix will be the R cross R between X1 and X2. And then again, you take a tensor product between X1 and X2 and X3 output. So what will be the dimension of the tensor product for that case, for final tensor product? Along which you want to take the tensor product? Along what dimension?
I think I missed something. Could you say that again?
Yeah, so here, like, can you mention just as simple as this, what will be the dimension of the tensor product? Suppose after you perform X1 and X2, for that you perform the tensor product. So, and what will be the dimension for the first two tensor product and the last one? So, and along what dimension you are taking the tensor product?
So let me try to explain. So if we handle one point, then output of this neural network is R dimensional vector.
Yes.
But if we add like n points here, then it's going to be n by R matrix.
Exactly.
Same thing for X2 and X3.
Yes.
And then n by R matrix, and you take the one column, is going to be this vector.
Column. Okay, so you are doing along the R dimension, the tensor product.
Along the R dimension.
Raj, I think he mentioned, Dr. Park mentioned outer product. That's somewhere.
In the paper, professor, it's written element-wise product. That was the confusion.
No, he just said earlier, outer product. So that's the thing. We don't have the code, Dr. Park. You didn't release it, so it's a little confusing.
Yeah, I think I promise I'm gonna release the code at some point. I will definitely very soon.
I mean, we're asking a question, you say maybe.
Yeah.
I know, no, I mean, I'm 100% sure I'm gonna release a code.
Yeah, because in the paper X1 you also represented as one element and as a vector also. That was very big confusion for me.
Yeah, we admit there are some errors in the workshop paper. But okay, let me clarify this.
Sure.
So one point goes to neural network. We have R dimensional vector.
Yes.
And if we have n points, then this network generates n by R matrix.
Yes.
Right? And we take one column of the matrix for each neural network, and then we do the outer product.
Okay.
And so we do this outer product for every column.
Okay.
Right. And then we have this guy, so n of these guys, right?
Yes.
And then we sum them up. That's going to be low rank optimization.
Okay. Okay. Yeah, I will give a shot with this explanation. So yeah, sure. Please move on. Thanks.
Yeah, and again, actually, one of my students are also here. So we promise we're gonna release the code anytime soon. So.
Okay. Okay. Sure.
Yeah. Okay. I'm gonna move on then. So before we go into more about SPIN, I'm not sure how much time I have. So we have 15 more minutes. So I want to recap the automatic differentiation. I think everyone knows about this in this talk, but sometimes some people, just take it for granted.
You don't, Dr. Park. You don't need to cover this. People know this. You don't need to cover.
Okay, I'm gonna then move on. So anyway, there are forward mode and reverse mode, and so what we actually use in neural net training, we are using reverse mode, which is also known as backpropagation, and this is really good because loss function is input dimension is high and output dimension is just scalar value. In the case of one backpropagation, we can compute the gradient of function with respect to the entire network parameter. So that's that reverse mode. And this is this is a simple example. So this is function one input dimension and 3 output dimension. In that case, if you want to compute dy dx, for reverse mode, we have to do 3 backward paths. So for y1, y2, y3. But if we use forward mode, we can do 1 forward passes, right? So this is one input, so we can do 1 forward pass. We can get all the gradients here. So in the right side, so 3-dimensional input and 1-dimensional output. In this case, 1 backward pass. But for forward mode, we have to do 3 forward passes. So 1 forward pass for x1, and the other one for x2, and another 1 forward pass for x3. That's forward mode and reverse mode. So let's take a look how it works in training pins. So here, let's say 3 by 3 by 3 tensor, and in total 27 points. And so normally, whatever you use, reverse mode or forward mode, we have to go through 27 backward and also 27 forward paths, no matter what modes you are using. So, but things get changed in separable pin. So we have, we put 3 points for each network, and then we generate 27 points here by merging, in this case, a tensor product. If we use reverse mode, we have to do 27 backward passes for each output point. But if we use forward mode, we can just do 9 forward passes. So because we pass through 9 input points. That makes sense. So for example, for these input points, if we do forward mode automatic differentiation, then we can compute the gradient of points in the first slice of the 3-dimensional tensor. And these second points, we can compute the gradients of all the points in the second slice. And similarly, for third points, we can compute all the gradients of all points in this last slice of the tensor. So in total, again, with only 9 forward passes, we can compute all the gradients here du dx, so which is very efficient. So, so in retrospect, so it's not that like we first suggested, separate architecture and then apply, forward mode automatic differentiation. So how we, came up with this idea is first we are thinking about, how we can apply, forward mode differentiation to make it, efficient computation for getting gradients, and then we have to devise network architecture. Then that comes down to the separated architecture. So there are some questions about the point structure. So because we are some Cartesian product of the points, the eventual points have some structure. So maybe left side of the figure, we call it as a factorizer coordinate, but that has some structure. And usually when we training PIN, we use some random sample location of collocation points. And then we have observed that if we have some structure, collocation points, there was some performance degradation. So what we did is that we can resample points every iteration. Then eventually we can cover entire domain. That's one issue about structure collocation points. And another question might come to your mind is some expressibility of separable PIN architecture, because it's not a naive neural network. It's a separated version, and so we sort of provide a theoretical study about we can approximate any functions in L2 space. This is not the part of the workshop paper. We'll update. So the later version will include this part. So if you are interested in the detailed proof, we can take a look. And
hello, this is Lulu. Sorry to interrupt. I just to mention, so I sent another paper in the chat. Actually, in that paper, although we focus on the operator learning case, but as special case, we also look at the function approximation. And that's for that special case, we also have basically the same architecture as yours, and we call it tensor network. Yeah, but that paper is also is focused on the operator learning, but that's a special case we propose in the paper. Probably got interesting to look at the paper.
Sure, I will definitely take a look. Oh, is it from your group?
Yes.
I see.
I put the link in the chat.
I see. I'll definitely take a look. Thank you. So anyway, so we manually calculate the flux using the approach in the reference. That's for 3D PD systems for Helmholtz and Klein-Golden equation. And the given 64 cubic collocation points, roughly in terms of flux meaning floating, the number of floating operation, and compared to PIN baseline, it's like 1,000 more efficient. So flux by definition is summation of number of adding operation and number of multiplications, and that we have like 300 megaflux versus it says 400 gigaflux, so it's about 1,000 times less computational cost, theoretically. This is experimental results.
Sorry, Dr. Park, may I interrupt?
Sure.
Yeah, could you go back to the previous slide? Yeah, here you say you have the cube of 64 collocation points, and could you go back to the previous slide? No, the one before. Yeah, so here you say you don't use, so basically it seems to me that you don't use the uniform sampling strategy, and but then why do you have the cube of 64 calculation points in 3 dimensions? So
that's,
yeah,
I mean that's for just demonstration purpose, and also so for implementation, if you make the same, if you use same number of points for each dimension, the implementation gets really easy. So that's all.
Yes, I get it. You get it, but does it mean that this randomly sampling or this sampling strategy applied to the 3 dimension or just 1 dimension? Then you repeat for 3 times.
So it's so let's say so uniform distribution for each dimension.
Oh, I see. Okay.
But if you do Cartesian product, that looks like this.
Yeah, I get it. Thank you.
And I've done this. So basically this, yeah, so the solid line is separable pin and dashed line is pin, but this is our implementation of pin. So our implementation might have some bugs or something, but anyway, we try our best. So mode means the modified MLP architecture. It has been used in many papers, as far as I know. So usually modified version improve performance generally. And this is convergence of the graph. And the y-axis is the log scale, as you can see. And as pin converges really fast, and the x-axis is not a runtime. It's an actual word clock runtime. So maybe 8 seconds, we get to a really low error. Compared to pin, it takes longer time to converge. Also, memory and runtime. So 64 cubic is the maximum points we can use for one in a one GPU. 128 or 256, actually we cannot use it for pin because it takes a lot of GPU memories.
Hey, may I? Hi, this is Adar from Brown. Can I ask a question? Do you remember which coefficient you used for the Helmholtz equation? Because like if you use the smaller one, it's very smooth.
Helmholtz, it has a little bit, it's a little bit higher frequency, I remember. Let me put the paper. By the Juno, do you remember?
Oh, so is your question is what exact value we use for the frequency?
Wavelength or something you used as a K for the Helmholtz?
Actually, in the published version of our workshop paper, I used frequency of 2 pi times 2.
I see.
For 2 dimension and 2 pi times 3 for 1 dimension. But actually in this graph, this is a new version of our experiment, and we used higher dimension. And I remember it was 2 pi times 4 and 2 pi times 5.
I see. That's interesting because these are pretty high, so it means that the function is very oscillatory and there should be interactions between the dimensions, and it's really interesting how it's getting captured in the product that you're taking afterwards. Okay, it's just a comment. Okay, thank you.
Thank you. And this is another experiment. It is Klein-Gordon equation. We try 3D, 2 plus 1D, so 1 is time dimension, and 3 plus 1D. And as you can see, the separable pin converges much faster. And for 4D, we barely train the conventional pin method. So that's this is one animation we made. So if you look at the solution function, and this is actual training time with the one GPU, like 20 seconds, you see really the solution functions. And we have tried, so this one, that's from Kozerpin paper. I'm pretty sure you guys are aware of this. So it's a 2 plus 1D Navier-Stokes equation, and this figure represents the initial condition of that equation. And we used the vorticity form. The reason is we wanted to do some fair comparison with the Kozerpin. And so they use the vorticity form. The other papers sometimes use velocity form, but we use the vorticity form. And U is basically velocity, and then we take the curve, and we get the vorticity here. And then this is a Navier-Stokes equation in vorticity form. And this is divergence free, and this is initial condition. And also it's a periodic bound. So setting is exactly the same as the causal pin. And this is the video I'm gonna play right now. This is a time at 0.2, 0.4, 0.6, 0.8. As you can see, currently maybe 20 seconds. Still is training, but you see it's really close to the reference solution. And here, reference solution, we get the exactly same solution from causal pin, and they got this solution from JAX-CFT software. So there are some tricks here. Causal pin use some time marching training scheme. Basically, they divide entire time domain into small intervals, and they train each network for small intervals. And we do the same thing. So although I show this in parallel, but they behind the scene, first we train this guy, and then we move on to the next stage, and we train next time interval and so on. But for demonstration purpose, I just put them all together in one place. So you train quite well.
So training time would be, because if you have to train one first and then go to the second, how does the training time reflects here?
So yeah, you're right. And so the one column represents just one time interval. So here, T.4 meaning we already trained up to time 0.3, and here 33 seconds means training only interval 0.1 seconds. Does it make sense?
So training time is for training the whole from very beginning to the end of the time steps, or is it just for each time step?
It's just for each time step.
Each time step. Got it.
Each time interval. Okay. And this is a quality. This is a solution after convergence. And although we have some errors, but compared to reference and our prediction, you are very close to the reference solution. Same thing for time point 1.0. We get a very close solution. And this is a quantitative results. And one thing I really want to mention is that we never use causal loss. The causal pin paper, they really emphasize that causal loss is really important to make it work. But using separable pin architecture, we don't have to use causal loss.
What is the NC?
That's the number of collocation.
So, oh, I see. But you're taking like much more.
Yes, here, but this second one, we use same collocation points. So errors are a little bit higher. So we can use more collocation points because we are computationally much more efficient, and it gets lower error. And if you compare actual runtime of causal pin and separable pin, so causal pin, so that's our estimation. We contact the author of the causal pin to estimate the runtime as accurate as possible. So that's probably right. So they take like 100 minutes, but ours takes like maybe around 10 minutes.
Okay, gotcha. Thanks.
So I have a question here. So for increasing number of collocation point, your memory usage is constant?
That's also very good question. So it's because of rounding of error. And
I couldn't hear you. So I think you're far from the microphone.
Please come near the mic.
I'm sorry,
I can't hear you. I think you're far from microphone. Yeah.
Can you hear me now?
Yes, it's a feebly, but that's fine again. So
yeah, so here memory, the most of memory comes from the final merging step when we actually build the 3-dimensional tensor, actually 4-dimensional tensor in this case. So this number of points really matter when we pass through the neural network, and that doesn't really affect the final memory because most of memory comes from the actual final solution. Hope that makes sense.
So this memory usage is at what instance of training? It's like during the AD, during the optimization. It is like total during the, it is a footprint, memory footprint, or it's just for a specific operation?
It's a memory footprint during training.
Okay, but it means 70 gigs for all the collocation point is, I don't see that why it is so. Yeah, okay.
Yeah, because we are using separate architecture. So even if this 2 to the 18 is the final number of points, actually, we are not really passing through this number of collocation points to the neural network.
Maybe you're batching and then you're only loading to the memory the batch of collocation points, and your batch size is the same.
I think batching is not the option here because it has to do the tensor product for entire domain. So it's okay. We will look into that.
All right.
Thanks.
Okay. So anyway, no codal loss for SP. So this is a final demonstration. So we have tested on a 3+1 Navier-Stokes equation, and we only tested on a manufactured solution of Taylor Green vortex something. I believe don't think I'm aware of this, but this solution function is sort of decaying velocity function. So here is a velocity fields, and as time goes by, the magnitude of velocity is decaying. And the first law is exact solution, and second law is our prediction. And so when we actually do these experiments, we didn't know that there's another paper who tried 3+1 Navier-Stokes equation, and we recently found that NS flow nets, I think it's from Brown University as well, and they also did the almost similar equation to test the PINN, but there are a little difference. So we are not able to do apples to apple comparison here. But final accuracy is 10 to the minus 3 something when we use 32 to the 4 collocation points, and we are able to obtain this solution in maybe around 30 minutes. So that's probably all I have. So there are some future works. So personally, I think if you really think about training PINN for high dimensional PD or some complex solution function, I think the separable PINN is a really good promising direction, in my opinion. And because otherwise we will not be able to scale this up, even if you use like maybe hundreds of GPUs. So scale really matter. Maybe if you think about 3+1 in Navier-Stokes in the terminus regime, so it's a 4D, and if you do like more than 1K resolution for each dimension, that's not really easy problem with conventional architecture. So we are trying to tackle this problem. And also I was told that there are also PDs that higher dimensional than higher dimension, such as like Decay equation. It sometimes goes up to 7 or 8, more than sometimes 10. And also, as you can see, the runtime, like we obtain maybe at best maybe 6 times efficiency, but flops, as I show, like 1,000 times more efficient. But there is a huge gap between this. That's mainly because how we implement hardware like cache or the software hardware. So these are systemic engineering problem, and I think this is really important to make the progress. So we also interested in this direction as well. And we
so Dr. Park, on that point,
right.
Your explanation is a little too vague. software and hardware issues. How do you go from 1,000 to 60? Can you pinpoint some issues?
Currently, JAX or PyTorch has very inefficient automated differentiation. That's first. And our current implementation has also some issues. And the other one is, honestly, I don't know. I hope to dig into details.
Because you show that your convergence rate is actually faster than the pins. So you are faster than pins. The mega flops, the flops is 1,000 times, but yet the final time is 60, which is, of course, it's great to have a clear factor of 60. I'm not complaining about it. I'm very happy, but I was just wondering, what's the bottleneck from your experience so far? And you say the autograd. I don't think that's the case.
To be honest,
can I give a short comment on that?
Yes,
sure, yeah, of course.
Oh yeah. Well, so what we think is that actually we don't think SPIN is not implemented in an efficient way, but rather we think that PIN is still faster even we use large number of collocation points, because what GPU does is that they process the specified coordinates in parallel. So actually in flops, in terms of flops, they vary 10 times, but we use GPU and we use parallelized processing. So PIN is still what I think is that PIN is still fast enough.
Okay, Raj, do you know what?
Yeah.
Don't
know, like I'm not there with them, but in the paper they mentioned that Jacobian vector product, which is forward mode differentiation, it is saving the time, but it's hard to fathom because in the Jacobian vector product, it doesn't give you the derivative, it gives you the directional derivative, and then to construct the derivative, you have to compose it with the unitary basis function. So it's hard to understand that how you are saving the memory there. That was main confusion with me, like because that is why we go for the combination of both the reverse mode and forward mode. So yeah,
so in terms of memory. So
Dr. Park, the question that Raj is asking is, here you demonstrated the forward pass only, right? But that will give you the function, the derivative, directional derivative, not the derivative, but you need the derivative for pins. So do you also use back propagation or not?
We do use back propagation when we actually compute the gradient with respect to network parameters. But when we compute the du dx, I don't think we use reverse mode. Am I correct, Juno?
Oh yes. We never used reverse mode autodiff in computing the derivative with respect to input coordinates.
Right,
no,
because it's only one direction.
No,
Raj,
in the
only one
paper,
next.
no, but in the paper they mentioned they use forward mode auto differentiation. That is Jacobian vector product. It's not the derivative. It's the directional derivative.
It's only one direction because they have separate x1, x2, x3.
Oh yeah. Also we use 3 Jacobian vector products for SPIN when we deal with a 3-dimensional PD.
Yes, that's my question, because when you do that, so you have to compute the column of the Jacobian matrices individually. So I'm not like understanding how the memory you are optimizing there, but because the size of the Jacobian is same there. Yeah, maybe we can look into that later, but that's fine. I think it's pretty late for you, so but that's fine.
So from my understanding, the main gain in the memory is so mainly because of the number of collocation points that we are processing. Because the PIN we have to do 27 points. And here we only have 9 points, but
sure, that's fine.
Anyway, we are going to release the code.
Sure.
And I think I'm done today, but this is I just want to advertise one more our work. If you're interested in, so we have also published a paper which is called Pixel. We sort of combine PIN and also conventional numerical methods, and so we take the best of the both worlds. And this is our first attempt, and we published this AAA this year, and we're going to present this work actually next week. So if you're interested, please take a look. And yeah, this is all I have today. I think.
Sorry, can you go to previous slide?
Yeah.
This is very similar to neural NGP, no? Or where you essentially encode the inputs with this voxelization in 3D or in 2D with discrete. And then the architecture is. Are you familiar with neural with NGP from NVIDIA?
Yes. That's
how is it? This is very similar. This is, I would say, actually exactly the same as neural as NGP architecture. No, how is it different?
It's the same.
The same. Okay.
But so yeah, actually the idea comes from the recent progress in visual computing area. If you heard about neural radiance fields, they are working on neural fields, which is just neural function approximator. But anyway, so we look at their methods and we realize that that's a really great combination of numerical methods and PIN. So actually we try, and then we discover this converges really fast because there's no actually spectral bias here.
Yeah, it does converge fast. I've been testing. So have you used the paper is published or archived?
Yes, it's published, and actually we open source everything, and I think we try really so much effort to implement customized CUDA kernel for this. So so it's working. So you can download the code and you can run it. It just
nice. Thank you.
Sorry, and yeah, that's all I have. And I think I already took a lot of questions, but if you have more, I'm more than happy to answer.
Yeah, thank you, Dr. Park. I think there's only one question remaining.
Code.
When will you release the code? And we are, since you already published the paper, when will you release the code?
That depends on Juno here. So when will we release the code?
I will release the demo code for the Klein-Gordon experiment within next week.
Okay.
You said you're sick today, but yeah, that's great.
I also maybe Lulu mentioned that he has this paper, which I know the paper that he has on the multi-operator. But Lulu, did you realize speed up factors of the order of 60 or 50 or 100?
I think Lulu left.
Okay. Oh, okay.
I tried that on DeepOnet, George, and yes, it speeds up. If we have separable pins on X, Y, and T, separable DeepOnet trunks for X, Y, T, it speeds up, but not by a factor of 10 or 100. You can say the working the speeding is like the time is reduced by almost 3/4. So you are doing it in 3/4 time. But I did not observe anything in the convergence.
Yeah, so we're very curious, Dr. Park, to compare our implementation of PIN with your S-PIN. I will be happy if you are correct.
I'm different. Okay, and so in terms of code release, so do you guys have, you know, NSFlowNet somehow available at some point? Because we wanted to compare.
NSFlowNets is actually Shenzhe's paper. Probably we also have that, or I don't know. George, maybe we can ask Shenzhe about.
NSFnet 1 has an NSFnet, yeah.
Okay.
And we did a 3D Taylor quit with both the vorticity velocity and the
right.
And the pressure velocity formulation. But that's not a difficult problem because the flow decays very quickly. And actually, Dr. Park's results were not correct. You could see that even from the third, they were not correct, even in the naked eye norm.
Yeah, and but you also try the turbulence regime, but very small domain experiment. So
yeah.
Do you remember that?
Yeah, it's not turbulence. Please don't repeat the mistakes of the past.
Okay.
Those who wrote turbulence for the first time know not fluid mechanics. Stephen Moore has a here. Stephen comes all the way from Africa, right, Stephen? Where are you now?
Yeah, I'm in Ghana.
He's from Ghana. I see you have an international audience. Hi, Stephen. Good to see you again.
Yeah, good to see you.
So if there are no more questions for Dr. Park, we would be closing our session today. So have a great rest of the day. Enjoy the winters with -20 and have a great weekend ahead.
Thank you for inviting me. Thank you. Bye.
Thank you very much.